Today I'm going to present Veil, a system that allows developers to strengthen privacy semantics on their web pages without browser-side assistance. This is joint work with James from Harvard and Nikolai from MIT. So all the popular browsers, Firefox, Chrome, Safari, etc., provide a private browsing mode. The point of this mode is to prevent storage of any identifiable persistent client-side state collected from pages browsed in this mode. Of course, this doesn't happen in practice. Research has shown private browsing modes are leaky. For example, the act of fetching a website can pollute the DNS cache with URLs of the web page and its external resources. Fragmented RAM artifacts, such as JavaScript and image files, in page swap or hibernation files, allow forensic tools to easily recover this data and fingerprint activity. The problem is that private browsing is hard to implement with only client-side support. One reason for this challenge is that browsers are complex and constantly adding new features, so it's hard for browser developers to understand how private session state is manipulated by various parts of the browser. Another challenge is that browsers lack a priori knowledge of what's sensitive in a page. At best, browsers could try to use crude approaches like mlocking everything to prevent page state from swapping to disk. But that's ineffective, because then the physical memory pressure in the system will just get huge. Even mere transmission of web content to a user can pollute in-memory and on-disk regions. So this brings up the question, what if web services and developers could enforce private browsing semantics by transforming a page's content? The goal of giving developers this power is to protect grubbable content from being recovered by post-session attackers, which is weaker than strict forensic deniability. The involvement of the web service in the private browsing workflow is based on the observation that web services, 1, control the content delivered, and 2, control the servers that deliver this content. In particular, we want to modify the web server and the web content so that the developers can implement private browsing semantics. With this goal and insight in mind, we designed a system called Veil. In Veil, there are 3 main participants: the developer, the blinding servers, and the content browser. The web developers have to opt into this framework. So here's how Veil works at a high level. The developer takes the HTML and external HTTP objects like CSS, JavaScript, and images, and runs them through the Veil compiler, which rewrites the website into the correct Veil format. Then the compiler uploads the rewritten HTML and objects into the blinding servers, which store and mutate content. Mutation obfuscates content to eliminate site-specific artifacts. When a user wants to visit a website, she first visits the Veil Bootstrap page and enters the URL she wants to visit. Then the Bootstrap page communicates with the blinding servers to load the page while hiding page-specific URLs. I'll go into more detail about each component later in the talk. So our contributions are the following. Veil, which is the first web framework that allows developers to provide private browsing semantics. We use techniques such as URL blinding, content mutation, and heap swapping to protect privacy. We have 2 browsing modes to provide different amounts of privacy. We evaluate on real websites, and Veil requires no client browser-side changes. So here's an outline for the rest of the talk. I'll talk about the Veil architecture, and then move on to the implementation and evaluation. So here is the overview of the Veil architecture again, before I dive deeper into the details of each component. First, I'll talk about the Veil compiler, which rewrites the HTML of an existing site. Then talk about the blinding servers and client browser workflows. So here's what the compiler does. Developer for foo.com creates a page as normal, generating an HTML file which references CSS, JavaScript, and images. The developer passes those objects to the Veil compiler. Here's what the Veil compiler outputs. First of all, for the CSS, JavaScript, and image files, it's going to calculate the hash value for each object. So for the JavaScript object, it starts with B6F, for example. Then it's going to rewrite the HTML file. The input version of the HTML has the expected tag for each of the external objects. The Veil compiler then replaces each one of these tags with JavaScript code that executes the special Veil fetch function. As I'll discuss later, Veil fetch is used to dynamically download an object with a particular hash name and dynamically update a page with the fetch content. The Veil fetch hashes represent blinded URLs, which are used to prevent DNS cache pollution. But what does the developer do with the Veil outputs? In the regular world, the developer uploads content to a web server that has the names of her website, for example, foo.com. In Veil, content providers collectively maintain a set of machines that we call blinding servers. These blinding servers all have the domain name veil.io, so fetching data from one of these servers doesn't leak any information via the host name. So the compiler uploads its outputs to the blinding service using the service's key value interface. The CSS, JavaScript, and image files are named by their hash, and the associated values are just the bits in the files. The key for the HTML file is its standard file name, for example, index.html, and the values is the bits in the file. So say we want to visit a site, foo.com. Let's see what happens. First in Veil, we don't type foo.com into the address bar. Instead, we type the address for veil.io, which is the domain name for the blinding servers. The browser generates a standard GET request for veil.io's index page, and the blinding servers return the veil.io bootstrap page, which prompts the user for the actual Veil page that she wants to load, and for her Veil password, which is used to derive a symmetric AES key. So now, how do we load a page privately in Veil? The Veil bootstrap page sends a GET request for the page that the user wants to load. However, note in the GET request, the name of the page to load is encrypted with the user's symmetric key. Also note that the GET request has a special header called Veil key. The value for this header is the user's symmetric key encrypted by the public key of the Veil binding servers. So a blinding server gets the request, decrypts the user's symmetric key, and uses that key to decrypt the name of the content that the user wants to fetch. In this case, that content is a top-level HTML page for foo.com's index page. The blinding server returns that content encrypted with the user's symmetric key, which is then decrypted in the user's browser. So remember that the HTML is just the output of the Veil compiler, so that HTML right now just has a bunch of Veil fetch calls in it. So how does the actual page load? So using JavaScript, each Veil fetch call recreates a tag from the original page. As that HTML executes, it issues requests for CSS, JavaScript, and images via the Veil fetch method. Once Veil fetch has retrieved an object, it uses JavaScript to dynamically insert the content into the web page. Once all of the objects have been fetched and injected into the document, Veil has recreated the original foo.com page without changing the top-level navigation bar to point to the foo.com page. Thus, the browser address history will never see the URL foo.com. A key technique we used is blinded URLs to prevent DNS cache pollution and safely allow for caching. More information about the properties of blinded URLs is available in the paper. So here is a summary of the techniques we use to protect RAM artifacts. We use heap walking and content mutation to scramble the page so that it's more difficult to recover the HTML. There are more details about this in the paper, but the motivation for these techniques is to not leak site-specific greppable content. One very important thing to note is that URL blinding, heap walking, and content mutation are inherently unimplementable by the browser, so we can't just implement Veil by modifying the browser. There is still one main source of leakage. What I described has solved many of the problems with private browsing, but the complex DOM structure of the original page still exists. We use heap walking and content mutation to reduce the likelihood of this and make it difficult to recover if browser state does swap to disk. If a site is not worried about this, standard Veil is sufficient. However, some sites might want to minimize client-side DOM state, so we developed another veil mode that provides more privacy called DOM hiding mode. We treat the user's browser as a thin client that only displays bitmaps and forwards browser events to a remote server. The remote server's job is to load the page, apply GUI events, and return screenshots of the page. I'll show you the actual workflow for loading a page in DOM hiding mode. The setup is similar. There's a bootstrap page on the client browser, blinding servers, and a content provider. However, the bootstrap page has a veil remoting JavaScript stub that will facilitate the loading of the page and processing GUI events. On the content provider, there is a headless browser to load the page and a veil GUI proxy to handle events. So what happens? The user enters in the form the page she wants to visit, foo.com, and user password, and sends it to the blinding server that forwards this information to the content provider, who then uses the headless browser to load a normal version of the page. The content provider takes a screenshot, sends it to the blinding servers, who forward it to the client. The browser now loads a screenshot of the page, and the screenshot can be mutated to prevent any fingerprinting. So what happens when we want to click on an element on the page, for example, a link? The user clicks, and the veil remoting JavaScript sends the click event to the blinding servers, who forward it to the content provider. Recall the normal page is already loaded in the headless browser. The veil GUI proxy does a click event in the headless browser, which loads the updated page. Then a screenshot is taken and sent to the blinding servers, who forward it to the content browser, which now displays it. So now I've given you an overview of the veil architecture. I'll move on to the implementation and evaluation. Veil has 4 components: a compiler, blinding servers, JavaScript library for bootstrap page and DOM hiding mode, and a GUI proxy. The compiler and blinding servers are written in Python. The GUI proxy uses headless Chrome, and we use Beautiful Soup to parse and mutate HTML. We evaluated Veil on 6 actual web pages. Here are the page load times for standard Veil mode without DOM hiding. As you can see, the overheads for using Veil are moderate, between 1.25x to 3.25x. We think this is reasonable because people are willing to use Tor, which has round trip times of over a second. The MIT page had the highest overhead. It's particularly challenging because it's a small page but had many images, so the crypto overhead was paid more frequently. Here are the page load times for Veil and DOM hiding mode for the same sites. The page load time is 1.2x to 2.1x higher, which is reasonable for the added privacy. So Veil is the first web platform that allows developers to provide private browsing semantics. However, it is related to a few other systems. CleanOS, Lacuna, and PrivX use secure deletion to implement privacy. More specifically, they encrypt sensitive objects and discard the key, which effectively deletes the objects. However, they require configuration and installation of special runtimes, but Veil does not. Also, they cannot protect sensitive data unless their abstractions spread across the whole system. Ucognito exposes a sandbox file system to a private browsing session. However, like the systems above, it requires a modified client-side stack, and it also doesn't prevent information leakage via non-sandbox parts. So to conclude, traditional private browsing modes still leak information. I presented to you Veil, which allows developers to improve privacy semantics of their web pages. Veil uses a variety of techniques, which are inherently unimplementable by the browser, to hide sensitive information from post-session attackers. And we evaluated Veil on various real web pages and found moderate overhead. Thanks, and now I'm open to any questions.
Thanks for the talk. Very interesting work. I have 2 questions. One is, How does your DOM hiding architecture compare to the architecture of things like the Amazon Silk browser and Google's mobile Chrome that also do a lot of the rendering on intermediate server?
Yeah, so I mean, kind of how it's kind of very similar because there's kind of a browser that's on the server, but I think the primary difference is like we have this kind of blinding server that kind of sits in the middle that kind of does a lot of forwarding, but kind of like a lot of the mechanisms are very similar. Like we use a headless browser, we take a screenshot, we kind of send it back, and then kind of it displays on the kind of user client.
And my second question is, I didn't really understand why you derived this k-user from a password, because you obviously send an encrypted version of k-user to when you get the request. So couldn't you just use any random key?
Yeah, so you can use any random key. The idea of kind of like deriving this key is that a user only has to type in a password instead of like mentally kind of have to write down 128 bits, right?
No, but I mean, couldn't you just send any key, or is that since you're sending the key encrypted URL and then you're sending the public key encrypted key?
Yeah, I mean you can use any symmetric key. I think the reason
But couldn't the JavaScript just pick a random key when you start up a browser?
Yeah. I mean you could, yes.
And that would have much higher entropy.
Sorry?
That would have much higher entropy than a password.
I mean it would have similar entropy because you would just like put it through PBKDF, like a key derivation function. I mean, it's just easier for kind of like the user to remember and use the same key every single time.
But why does the user need to use this? So this is what I don't understand. Why does the user need to use the same password?
Why does
like, can't I use a different password tomorrow than I did today?
Okay, yeah, sorry. So kind of something I didn't bring up kind of in the talk, but it's in our paper. We actually allow for caching, so we have an encrypted cache that gets decrypted on the client browser, so that right now what I've described is like something that's cold. It's not kind of like.
So if you use the same password, you can use caching.
Yeah, you can use caching and it can decrypt, so you don't have to kind of make a lot of these round trips.
Okay, thanks.
Yeah.
Good, Frank, really exciting set of ideas. I'm wondering if you can generally comment on potential limitations of the architecture. I think there are three categories that quickly come to mind. One is about incentives. So what incentives do web developers have to protect user privacy? Usually, they're more interested in collecting data about users. The second aspect that came to mind is in terms of the user experience. So you mentioned that the address bar stays the same, veil.io. So I'm wondering if it has implications for things like phishing attacks and so on. And more generally, is it compatible with advanced web functionality?
Yeah, I mean, I think to kind of your first question, what was your first question around?
Incentives.
Incentives, yeah. I mean, I think kind of when you look at certain websites, pride themselves on privacy, like, kind of like, a porn site or kind of an adult site, or certain sites, a lot of people are willing to pay for privacy, as you can kind of see nowadays. Like, people are becoming more aware using DuckDuckGo. So I think sites that kind of provide privacy will, establish better trust with users, and that's kind of something we hope for. The second question around kind of like the user experience. I mean, I think, it's obviously not as good, but, kind of user experience on browsing is kind of like a dynamic topic. So, kind of like Tor also doesn't have a great user experience on the performance side too. And so we think, users who are very privacy conscious, or, this could be used in a case where it doesn't have to be used all the time maybe, but, why people are on a shared computer, for example, that works out. And so kind of around your third question around advanced functionality, I mean, we kind of have some stuff in our paper about dynamic content. It's a little bit trickier. There's a little bit forwarding, some extra work you have to do. Same with kind of like cookies. I think kind of like there's a lot of still trickiness around kind of getting this to kind of work at the same smoothness level as kind of like, a Chrome browser, which, hundreds of engineers have spent like a lot of time kind of trying to get down. So yeah, I mean, I think there's still a lot of work to be done.
All right, great, thanks.
Cool.
Any other questions for Frank? All right, this concludes our session on privacy and de-anonymization. Let's have a round of applause for all of our speakers.